here, but all right. Is there anyone who's joined, or do you see anyone there? Okay. Let me give you a brief introduction to the course. This course is called the Topology and Condensed Matter Physics. And the aim of the course is to merge two apparently different topics, one that pertains to mathematical physics or which deals with the geometry of objects and shapes of different shapes, and what are their relationships with condensed matter physics. This really emphasizes that. So a number of important things we have been or would be talking about throughout the span of the course or duration of the course. And one of them is how topology actually enhances or enriches our understanding of different condensed matter systems. For example, the quantum Hall state is an ideal example of a topological insulator, which means that it is insulating in the bulk of the material and has edges that are conducting. So this means that the bulk of the system and the edge, they behave differently. I mean, the edges of the system, they behave differently. And this is an important thing. And if the bulk is, bulk means the entire inside of the sample. If it is insulating, which means that it doesn't have any transmission property or transport properties. However, the edges have conducting states, and this makes it a topological insulator. And we have given a number of topological insulator, which are mostly crystalline, that we have talked about here. And these crystalline insulators are protected by certain kind of symmetries, and these symmetries are mostly the discrete symmetries that we talk about, and not the crystalline symmetries. In fact, the crystalline symmetries play a different role, which is not discussed in this course. But the discrete symmetries, such as inversion symmetry or time reversal symmetry or particle hole symmetry, and sometimes combination of some of these symmetries are called as the chiral symmetry. And these really give a very important they protect the topological properties. And when they are broken, in some sense, you can break them either externally or you can break them internally, that is by introducing some disorder or impurities and so on. Then the parent symmetry is lost, and then hence the topological property is lost. And what we mean by the topological property of these materials, that is exactly what we have said, that the bulk of the material is insulating and the edges are conducting. And we'll see that, or rather the edges are special. I mean, there are special edge modes that are present in the system. And these modes are characterized by conducting properties. And we have done a number of examples of that kind, and these are usual simple tight binding systems, and that's how they are called as topological insulators. And there are other examples of this, and then we have talked about weak and strong topological insulators. We have talked about quantum Hall systems, spin Hall systems. We have talked about, these tenfold classification, which gives a general guideline as to how a system becomes a topological insulator, or why it's called a topological insulator. So I'll be happy to take questions. And this course courses, one of its kind. It doesn't exist in the NPTEL platform as yet, and it's a slightly advanced course on condensed matter physics, and which anybody who's planning to take up this condensed matter physics as a research topic would be benefited by this, whether it's an experimentalist or a theorist. So I encourage you to ask me questions, clarify doubts, and anything that you want to ask about the course. There's one question on the portal about symmetries. I'll answer when I get an intimation that someone who asked that question is around. Let me tell you what who asked that question. Suman De. Suman De, if you're around, you could rephrase your question or I can answer you. Any questions among the ones who are watching? Swati, yes. You're asking whether it's easy or hard to study. Well, I'm not too sure. Swati, what is your background? If you are not a master student in physics, then it's definitely difficult. Even otherwise, it's not easy, but it's interesting to learn how topology is connected with material properties. So, if you know a few basic properties of the materials, then you can predict the kind of transport properties that would exhibit, or even other properties. So it sort of depends on your background and what you intend to do. So I assume that you're a master's student. Yes, then it should not be easy, but it should not be hard the way I have taught throughout the course. I've tried to make things as easy as it can get, and tried to simplify things, give a lot of derivations, and BSc physics student, it will be quite difficult. It will be quite difficult. You, if you're a BSc student, your condensed matter or solid state background has not been very sort of, you haven't learned much yet. So it will be difficult, very difficult, in fact. By the way, I'm not teaching topology in the sense that topology is a branch of mathematics. I'm just using the topological aspects of that subject, or rather that subtopic, and how that is connected, or that sort of governs the physical properties, is what I want to teach in this. I'm glad that you are going through all my sessions, and you can ask me questions. If there are any specific questions, you can ask. Anyone else? Okay, you came to know about this. But this course is, as I understand from your background, this course is not for BSc students, really. You need to know enough quantum mechanics, you need to know enough solid state physics, band theory, and all that before you could do this course. It's for, final year master students and maybe PhD students. It's mostly for PhD students. Yeah, if you study from now, it will be easier to study. Yes. Yeah, yeah, that is true. If you study topology now, it'll be easy, but then you need to have required background of many things that are used in this course. Yeah, I know. I, I can't do anything about it. Probably it's a weekday, and people have school. I mean, colleges and universities. If you have questions, please go ahead and ask. You haven't asked any technical question. I don't know whether it's compulsory. It's floated as as an I mean as a help means of help to students. What do you want to know about the details of final examination? Suman Day, are you around? Can you hear me?
Yes, sir.
Okay, so you asked me about questions related to the symmetries, right?
Yes, sir. Yes, sir.
Okay, so let me give you an example of breaking inversion symmetry. So if you have a defect in the system, a defect means which changes the environment. Say in an array of copper atoms, if you put a zinc atom, then that breaks the inversion symmetry. That is considered a one-dimensional chain. So the right and left symmetry of or any atom is broken now, because the one that's on the immediate, next to the disorder or impurity doesn't see the left and right environment to be same. It sees, say, on the left, it sees zinc impurity, on the right, there's a copper. So that's how the symmetry is broken. And if you want to know how symmetry is broken, time reversal symmetry is broken by the magnetic field, there are two ways to understand it. One is that you can simply think of Maxwell's equation, which is a curl of B equal to mu 0 J. Let's not even talk about Aarti. Let me just come back to you in a moment. Okay, I'll just be joining you in a while.
Sir. Okay. Okay.
No,
okay.
Suman, I'm answering your question.
Okay, sir. Okay.
So there are two ways of understanding it. One is that just look at this Maxwell's equation, curl of B equal to mu 0 J. I'm not talking about the displacement current term. It could be there, especially in time varying situations. Now, J is current density. So current is charged by time. So in time reversal symmetry, if you do a time reversal, then the charge will be remaining as charge, but the time will change sign. So the current will change sign. So the current density will change sign. And for the equation to be still valid, so B has to change sign on time reversal, which means that it's odd under time reversal. There's another way that you can understand this. That is, the time evolution of any stationary state is given by exponential I et by h cross, where E is the energy.
So you have to remove some block.
Now, when you have magnetic field into the system, you have this wave function that picks up another phase, which is like an Aronoff bomb phase, like an exponential I A dot dl, where A is the vector potential associated with the magnetic field. So now if you do exponential I omega t and look at t being plus or minus, it'll have a phase which is I phi minus I omega t or I phi plus I omega t, and they're not same. So magnetic field indeed breaks time reversal symmetry. Okay, in SSH model, for example, if you replace a carbon atom by something else, that breaks the inversion symmetry, because the inversion symmetry center is between the two carbon atoms, is basically at the perpendicular bisector of the bond that joins two carbon atoms. So that's how it is broken. Aarti, the examination will not be MCQ. It will be descriptive, but you don't have to write long stories. You have to only write very short answers, which are mostly like fill in the blanks, you work out something, or there are some small short answer type questions that are there. I hope that answers your question.
Sir, can I ask one more question?
Yes, please. As many questions as you want, you can ask.
Okay. Sir, as you know that, as you already taught us that to get some topological invariant, okay, so like the Jack phase or the chart number is in 2D formation or Jack phase in 1D, like that. So to get the trivial to non-trivial transition means the trivial like something like mirror or something, and non-trivial means topological. There is a state formation. So to get trivial to non-trivial, there are some classification I read about in some paper. I am a PhD scholar. Okay.
Where are you a PhD scholar, in which place?
Calcutta University. Calcutta University.
Okay, very nice, very nice.
Okay. So and I am doing some work on the topological photonics.
Okay. So that's how you use Jacques phase and all that. By the way, Jacques phase is also defined in 2D. There is someone called Wakabayashi who has defined Jacques phase. In fact, it's nothing but the Berry phase. So in principle, it should be defined in any dimension. Anyway, you ask your question.
Yes, sir. So I read about some papers and they told that depending on there is some classification of the topological trivial to non-trivial transition depending on the class means some topological non-trivial to trivial to non-trivial transition is depend on the time reversal symmetry breaking. Some depend on the inversion breaking. Okay. Some depend on the chiral symmetry breaking. So how we can see a material or some geometry that it is depends on the chiral symmetry breaking like topology, trivial to non-trivial, or the time reversal symmetry breaking. Means I want to say that in a material, how we can choose like that it is time reversal symmetry breaking and there is a trivial to non-trivial transition, or there is a chiral symmetry breaking, trivial to non-trivial transition.
Okay. Yes. Okay. So you have to understand depending on what is, have you intentionally broken the time reversal symmetry, such as by introducing a magnetic field, or what you mean maybe is what Holden did. In a Holden model, Holden did a breaking of the time reversal symmetry by introducing a second neighbor complex hopping. Okay. So then it's not clear that whether you would have a trivial to topological transition, because some symmetries get broken means probably there is a lifting of the spectral gap or the spectrum changes. Maybe it was already gapped and it becomes more gapped. And then there's nothing interesting that happens. But in most of the things that we have studied, that we have seen that when you break certain symmetry, for example, in graphene, if you break inversion symmetry, nothing happens. There's no trivial to topological transition. This has been shown in the course, during the course. Okay, but if you break time reversal symmetry, then there is there's a transition that happens from a topological to trivial phase, and the system acquires, depending on certain parameter range, which is that if you study Holden model or if you study my lectures, you'll see that the M, which is called as the Semenoff mass, equal to 3√3 T2. That is the defining parameter below which there is a topological phase and above which there's a trivial phase, which means that is the gap closing condition. So the gap has to close and the gap has to open, and there'll be some symmetry breaking involved. Okay, so that is the main message, or rather the central point of discussion of topological transition. Now, what are these and why they, would cause these edge states to appear and make a topological insulator? That will have to be understood from, there is something called a tenfold classification, which I have taught as well in the course. Yes. So this, there are three parent symmetries, which are inversion, particle hole, and rather we call it chiral, particle hole, and time reversal. Now this inversion and chiral, this is a little confusing at times, But for most of the systems that you come across, such as Kitaev model or this SSH model, the inversion and the chiral, they mean the same thing. Okay, but it may not be. In fact, if you put a finite chemical potential in Kitaev model, it breaks the chiral symmetry. But chiral symmetry may not be a very important thing in some system, but it may be something very important in another system. So in SSH model, I hope you have, you know what is SSH model.
Yes, sir.
So in SSH model, if you break chiral symmetry, then you lose topology. It's no longer a topological insulator. But in Kitaev model, if you break chiral symmetry, you still have topology because the particle hole symmetry is intact, which is the defining thing of for the Kitaev model. So it is absolutely not a priori clear that whether you'll have the trivial to topological transition if some symmetry is broken or all the symmetries are intact and so on and so forth. For that to understand, you refer to this tenfold classification scheme that I have worked out, or you can look at what's called as Altland-Zinnbauer scheme. That will give you a very clear idea that what are the symmetries and which when get broken, you get a topological phase or you don't get a topological phase.
Okay. Sir, so can I say something? Okay.
Yes,
okay.
Please go ahead.
Okay. If we want to check what kind of symmetry can be broken in a material or a geometrical structure, so can we first visualize their Hamiltonian and then operate the symmetry operator on that? And if we get the same Hamiltonian, there is no symmetry breaking. And if there is no we do not get the same Hamiltonian, then we can call that there is this kind of symmetries break, and we can see that there is a trivial to non-trivial or non-trivial to trivial transition. So this is the process.
Yes, absolutely. You have to write down the Hamiltonian, the relevant Hamiltonian, check whether all these three discrete symmetries such as particle hole, time reversal, and say inversion is broken or not. If it is broken, that does not guarantee that there's a trivial to non-trivial or non-trivial to trivial transition. If it is broken, then you have a hint that it could be that there is a transition, a gap closing transition. But if you have that, then the second test that you have to take is that whether there are edge modes that appear into the system.
So you have to do the modal analysis or something, wave analysis.
Yes, you can say wave analysis for in your optics terms. Yes. Okay. And you have to find that these modes or waves that you're talking about, they are resilient to local perturbations.
So we have to input some random disorder something in a system, and if the state are robust against this disorder, then we can say that this is a topological state.
Yes, but not in SSH model. As I say, that in SSH model, as soon as you put in disorder in one of the atoms, say let's call it a carbon atom or whatever atom that you want to call it. In SSH model, the moment you put a disorder, you break the chiral symmetry and topology is gone. You can't study topology any longer. So whether it's T1 greater than T2 or T2 greater than T1, it's always trivial. It's an insulator, just a normal band insulator.
Okay. And so this kind of calculations is for all, this is in 1D, 2D or 3D. Means if we want to check this kind of, it is
all dimensions. In 1D you have the modes are like localized at points. So you have point modes. In 2D you have line modes. okay, which are called as edge states or whatever. And then in 3D, you have surface states and so on.
Okay. 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 And sir, one thing, if I have some question, can I mail you?
Yes, please. That is easier. That is much easier. Please mail me any question that you have, and you would get an answer immediately. Because this discussion forum, sometimes the TAs they follow, but there are some questions which yesterday I get them replied. I don't know whether they're from you. It was about. It was more about in some, about Hilbert space and Fock space and so on. But if you have any question, just ask me. So your work is on topological optics or topological photonics.
Topological photonics. I have already published a paper on the H model also.
Okay. Oh, very nice. Okay.
So lattice means the optical lattice.
Optical lattice. Yes.
So yes. I am doing the all topological thing in 1D, and my work is to apply the 1D topological model, especially H model, in a device formation.
Yeah. So you're talking about the Aubrey-Andre Harper model.
Yes.
Okay. Good.
So, sir, I will mail you whether I got some.
Yes. Please.
Okay.
Yeah, sure. To other learners, if you have any questions, please do ask. Is this a part of your coursework, Suman?
No, sir. I am my final year in my PhD now.
Oh, you are in your final year. Oh, I'm so sorry.
Yeah, but the main thing is that I am habituated the Maxwell's topology, not the Hamiltonian formation from the condensed matter point of view. So I have to build my potential in condensed. That's why I took your course.
Okay.
So I did not get any course from my starting point. This kind of as your course. Okay, so that's why I have to learn the electronic point of view, because I have to doing my research in future like that topological spinotronics or something like that. So that's why I took your course.
I understand. Yeah, there are a lot of actually research going on in photonics, topological photonics.
Yes.
In fact, you make arrays of waveguides and so on, and then these are seen as topological materials. There are realization of edge modes present in the system. The field is picking up very fast.
Yes.
Right. So you understood my this explanation on this time reversal symmetry and I mean magnetic field. Why does it break time reversal symmetry?
Yes, sir, but I have to read the book also because.
Yes. Let me just rewind once more. Apart from the Maxwell's equation, that's easy to understand. But you know that in presence of a magnetic field, the wave function has a phase, right? Another phase which is not, which is not the dynamical phase. It's like exponential I phi, where phi is nothing but the line integral of the vector potential, which is nothing but by Stokes' theorem, that's nothing but the B dot ds, which is the flux. So this phi is exponential I phi, where phi is really the flux quantum or whatever you want to call it. Now that makes the other phase, the dynamical phase, when you change t to minus t, the wave function does not remain invariant because you have an additional phase. So it's exponential I phi plus exponential I omega t. Now, if you change t to minus t, it will become exponential I phi minus exponential I omega t. I mean, exponential minus I omega t. They are not the same. And that's why you cannot have time reversal symmetry in presence of a magnetic field. However, in an electric field, you can have. Electric field does not break any time reversal symmetry. Again, you can see that from the Maxwell's equation. Okay. So your curl of E equal to 0 and your divergence of E equal to rho over epsilon 0. So rho is the charge density, which is does not change with time. Okay, so yes, that's invariant. So E is invariant as well.
So sir, so I read about something that it is called. It is not. I think you are approaching 2D, but I want to say something about that. That there is called a gyromagnetic material in topological research. Okay. So in gyromagnetic material, some paper they use the gyromagnetic material and then use the magnetic field, and they got the time reversal symmetry breaking. And I think the Halden and Raghu published a paper in 2007 on that.
Yes. I vaguely remember that paper, Raghu.
Yes, sir, that is the. I think that is the starting point of the topological photonics from the topological insulator.
Correct.
But in gyromagnetic material, the Hamiltonian, we can create the Hamiltonian of a gyromagnetic material. But how we can define, that is not understood by me till now, because I am not that condensed matter person. Okay, so I am from the solid-state electronics background, totally from BTech MTech.
Okay.
BSc BTech MTech, and this kind of thing. So, so I have to learn that because that is the main essence of the topological formation. Okay, so there is some operator called time reversal symmetry operator, as you told about in your lecture. I think in lecture 2, I think. Okay. So how the time reversal symmetry operator we can define for a gyromagnetic material and operate them in a Hamiltonian.
I have to see this. This offhand I cannot tell you. This thing I just knew about that work at that time. But after that, I haven't followed it up. I'll have to see this.
Okay, no problem, sir. No problem. Okay. Yeah. So there is a gyromagnetic means there is a operator, no? Means to operate the Hamiltonian. Okay.
Yeah. So, Jonty, I think there are no questions from the audience who have joined. So we probably can wind up. I'll give you 1 or 2 minutes if people who have joined the YouTube, if you have any questions, please do ask. Otherwise, we'll wind up. Jonty, are you there? Jonty, are you there? NPTEL office? Okay. I don't think there is any other question. It's more than 52 minutes have gone by. Okay. Because they have not asked any question, any relevant question in the YouTube. I mean, there was not a single question. Okay. So, Suman, if you can carry on with this thing because okay. You could ask me whenever you have any doubt. Okay.
Okay.
So,
okay.
Yeah.
Okay. Thank you.
All right. Then it's better to wind up, right, Jonty? Because I don't see any question. There are still 5 people watching, but it doesn't seem that they have any question or any relevant question for the last more than 50 minutes that we have been here. Okay, then. All right. Okay, bye. Yes, there is an application for spin battery. Spin battery. I mean, spintronic device. Yes, the topological material, insulating material has on spintronic devices, whether you want to call them a spin battery, but yes, you can probably call them a spin battery because that creates a divide between up and down spins on either sides of the or transverse edges of the material. Yes. So there's spintronics, topological insulating material can be spintronic materials. Vasant Kumar, if that is your question. So last 1 minute, if you have any question, please do ask. Otherwise, we'll wind up the session. There is roadmap of achievement of spintronics, definitely. I mean, there are definitely a lot of efforts to get them to make them, for practical utility, but usually you need a strong spin orbit coupling. Now that strong spin orbit coupling is not guaranteed in all materials. They get screened due to various reasons. If you can somehow, by external means such as gate voltage or using some electrolytes, etc., if you can induce a strong spin orbit coupling, then it probably can be. But there are a lot of research going on, and 2D systems are still thought to be good examples of spintronic, or rather they would give spintronic materials, but it's not clear whether, because as 2D materials, the spin orbit coupling is somewhat inherent and they don't get screened out so easily. But for example, in graphene or some of the variants like phosphorine and stannine and other things, arsenine, the spin orbit coupling is still pretty small, pretty negligible in some sense, so that they're not very useful in making spintronic devices. All right, then. I think there are no questions. Jonty, we'll just close it then. Okay. Thanks, everybody, for joining. Thanks, Suman, for some real physics discussion. We'll meet until next time. Okay, then.